Hi everyone! In this video we're going to look at graphical misrepresentations of data. So we're going to look at a number of examples that have graphs that can be misleading and just talk about them a little bit. So here's just a quote for you. Statistics, the only science that enables different experts using the same figures to draw different conclusions. So here's our first example. This is for a home security system, and it develops a summer ad campaign with the slogan, "When you leave for vacation, burglars leave for work." And according to the city of Minneapolis, roughly 20% of home burglaries occur during the peak vacation months of July and August. The advertisement contains this graphic, and then explain what's wrong with it. So taking a look at it, we have that July through August, or July and August, it's a little confusing which one it's saying, has 20% of the burglaries that occur. And then all other months is 8%. And so we can think, okay, wait, is this saying all other months combined, or all other months, that's 8% of the burglaries occur in each of those months? So it's a bit ambiguous. So let's consider how the categories of data are defined. The sum of the percentages, or the relative frequencies, which we've talked about before, over all 12 months should be 1. Because remember, we want 100% or 1 as in decimal form for our percent or relative frequencies for our data. So if you take a look at this computation, it does total 1 if we take the 20% for the months of July and August, and then we say that the 8% corresponds to the other 10 months of the year. So it's saying 10 times 8% for each of those months. That does total 1. So that lets us know that this does represent an average percent for each of those months, while the bar for July through August represents the average percent for those months combined. Basically what's happening here says the unsuspecting reader is misled into thinking that July and August have a burglary rate of 20%. So let's take a look at what would be an accurate visual for this. So this figure gives a better picture of the burglary distribution. The increase during the month of July is not as dramatic as the original figure made it look. And then if you notice, August actually has fewer burglaries than some other months, like September and October. The original figure would be considered deceitful because the security company was intentionally trying to convince consumers that July and August are much higher burglary months. So what they did was they took the percent of burglaries in July and added them to the percent of burglaries in August, which if you notice, that's this might look roughly around 11%, and then August looks roughly around like 9%. So they added those. That's where the 20% came from. And then what they did for the other 10 months of the year is they took their average. So on average, the other 10 months of the year had an 8% of the burglaries that occurred. So it was a very misleading visual for the data. All right, let's try another example. A national news organization developed this graphic that illustrates the change in the highest marginal tax rate effective January 1st, 2018. Why might this be considered misleading? So the highest marginal income tax rate in 2017, it looks like, was somewhere 39 point something percent. And then 2018, down here at 37%. Based on the height of the bars, it looks like a drastic change. But what I want you to notice is that we don't start at 0. Notice we're starting at 36. And so this gap between 37 and 39 looks really large, but it's really not that large in terms of the numbers. So it can lead readers, this graph could lead readers to believe that the tax rates are almost 3 times as high in 2017 as they were in 2018, since the height of the bar is almost 3 times as big as the height of this bar, when in fact the difference is only 2.6 percentage points. Okay, so this was in 2017, this was 39.6%. 2018, this was 37%. And so the reason why you can get an incorrect conclusion from this visual, this graph, is because our vertical scale does not start at 0. So notice that this would be a more accurate version of the graph. If we start at 0, notice that they're really actually relatively close to each other. So the mistake or the misrepresentation was the scale on the vertical axis made it look like the gap was much larger. All right, next example. The time series graph in this figure depicts the number of residents in the U.S. living in poverty. Why might this be considered misrepresentative? So take a look at the horizontal axis, that's years. And then on the vertical axis, this is number of people in the thousands. Okay, so let's kind of look at it and then let's see what we can come up with. So the graph may mislead readers to believe that the number in poverty has more than doubled from 2007, which is right here in about the middle of the graph, to 2014. And that's because the bar for 2014 is twice the length of the bar for 2007. Again, this is similar to the last one where our vertical axis doesn't start at 0. So this type of scaling is common when the smallest observed data value is a rather large number. It's not necessarily done intentionally to confuse or mislead the reader. Often the main purpose in graphs, like particularly the time series graph, is to discover a trend rather than the actual differences in the data. So sometimes this, like we just said, it's not done intentionally to mislead people, but if you kind of notice that from 2000 to 2017, all the values are between this 30,000 to times 1,000, basically, to 50,000. So it's sort of like a zoom in on the values just to see the trend or the change. So it's not necessarily meant to misrepresent the data, but it actually does. So the author of this graph should clearly indicate that the graph does not begin at 0, so including some kind of symbol on the vertical scale. This symbol indicates that the scale has been truncated and the graph has a gap. So notice just right here, this little symbol saying like the graph got truncated and all the values between 0 and 30,000 are not represented necessarily on the graph. It's like the graph is like smashed down vertically. So there's some things that could be done to make this display better. With this time series plot, it might be better to use a different form to view it other than a bar graph. Also, percents might be more useful rather than actual numbers of people because populations increase each year most of the time, and so the percent might be more meaningful. If the number of people in poverty goes up, it might just be proportional to the new people on the planet that now exist in the next year. So this is another version of the graph. Okay, and so it's a time series plot, and it's in percent form. So percentages of U.S. residents living in poverty. The lack of bars allows us to focus on the trend in the data rather than the relative size or area of the bars. So this one helps us understand it a little bit better and not get confused with the height of the bars and things like that. So this would be a better representation for the data. And again, notice that we are in percentage of the population instead of the actual number of people. All right, let's take a look at this one. This bar graph is a survey that was conducted by the Impulse Research for Quilted Northern Confidential, in which the individuals were asked how they would flush a toilet when the facilities are not sanitary. What's wrong with the graphic? So how we flush public toilets. 41% said they use a shoe. 30% said they act normally, I guess push it with the hand. And then 17% said they would use a paper towel. Okay, so let's see what we can figure out here. First of all, it's unclear whether the bars include the roll of toilet paper or not. So just the fact that they got creative with the toilet paper for the visual, it's a little bit confusing and misleading. So in either case, the roll corresponding to used shoe should be 2.4 or 41 out of 17 times taller than the roll corresponding to paper towel. Okay, so that's like the proportion, 41 over 17, the proportion of the height bigger than this one. If we include the roll of toilet paper, then the bar corresponding to used shoe is less than double the height of the paper towel data over here. If we don't include the roll of toilet paper, then the bar corresponding to used shoe is almost exactly double the height of the bar corresponding to the paper towel. So the scaling is just confusing and incorrect. All right, here's another one. So soccer seems to be losing popularity as a sport in the US. In 2010, there are approximately 14 million participants, and then by 2017, this number dropped to 12 million. To illustrate the decrease, we could create a graphic like this one shown, and then think about how this could be misleading. So this one is based on area. So they're saying in 2010, the area of this soccer ball represents the 14 million participants, and then it decreased to 12 million, and that would be represented by this soccer ball's area. But notice it looks like a drastic decrease based on the size of the visual and the size of each soccer ball. So the graph on the left for 2010 has an area that's actually more than four times the graph on the right, this little soccer ball. Well, the number of participants is given in the problem statement. They're not included in the graph. So we don't have, without reading the sentence, we wouldn't know that this represented 14 million and this one represented 12 million. So this makes the reader rely solely on the graphic to understand what happened. And so there was a 14% decrease in participation from 2010 to 2017, and not more than the 300% indicated by this graph. So this is very misleading because of the proportion size of each ball. The correct graph of 2017 should have an area that's only 14% less than the area of the graph for 2010. Also, adding data values to the graph would make it better understandable. So a variation on pictograms is to use a smaller picture repeatedly, with each picture representing a certain quantity. So for example, we could present the data that we just talked about, where a smaller soccer ball represents 1 million participants. The resulting graph would be here, and then notice how the uniform size of the graph allows us to make more accurate comparisons of the two quantities. So this is much more understandable and not so misleading. If each of the balls represents 1 million, we can obviously tell that this was 14 million in 2010 and then 12 million in 2017. Okay, here's another one. This figure represents the educational attainment level in 2017 of adults 25 years and older who are U.S. residents. So let's see. Remember, this is a pie chart, and if you notice right away, there's a couple of issues. If you were asked to answer something about this, it'd be kind of hard. If you were asked which level of education was the highest attained or the most often, because there's no percentage values given, that's pretty difficult to do. And because this angle of our pie graph, this 3D angle, makes it difficult. So three-dimensional pie charts tend to overstate the significance of categories closer to the reader. So for example, the category graduate or professional degree looks about the same size as the high school diploma category. Yet if you look at the raw data from the table, okay, so for high school diploma, it's 60,000. For graduate degree, it was 27,000. So they weren't nearly as close as the visual made them appear, close in size. So in fact, if we rotate the pie chart to bring the category some college, no degree to the front, we have this figure. So basically this 3D view, anything in the front just looks larger. So this now some college, no degree appears to be the largest piece of pie. And so the three-dimensional representation distorts the number of individuals in the category, so we should avoid these types of graphs. So here's a better one, two dimensions, and we have the percentage values. So this is much more understandable for someone looking. Okay, so just some guidelines for constructing good graphics. You want to title and label the graphic axes. So make sure that people know what they're looking at on the vertical and horizontal axis, like what's represented. And then units of measurement are also very useful. And then avoid distortion. Never lie about the data. So don't intentionally try to distort the image just to make the data seem like it says something different than it should. And then minimize the amount of white space in the graph, and then use the available space to let the data stand out. If you truncate the scales, make sure you just indicate that, like we saw with one of the examples. And then avoid clutter, such as excessive grid lines or unnecessary background pictures. Don't distract the reader. Also avoid 3 dimensions. 3-dimensional charts look nice, but they actually distract the reader and are often misinterpreted. And then do not use more than one design in the same graphic. Sometimes graphs use a different design in one portion of the graph to draw attention to the area. So don't try to force the reader to any specific part of the graph. Just let the data speak for itself. And then avoid relative graphs that don't have data or scales on them. Okay, that's it for this one. Thanks for watching.